and
it might be on.
The theory that I'm going to present is eccentric, and I take a consolation in the fact that although it is not yet at the center, it is within the perimeter. And I thank my friend Lucian Hardy for his kind invitation. The motivation for this work comes from many years of working on problems in quantum mechanics and relativity theory that bear on the nature of time. I've been intrigued by the fact that there is something about time. I would say the most clear, the most salient aspect of time that has no trace at all in the physical formalism. The fact that time seems to be moving, passing, that there is a flow of time, that there is change, has no trace, neither in relativity, I would say, nor in quantum mechanics. On the other hand, people who are searching for a unified theory are very generous and exercise huge imagination, invoking all kinds of extra dimensions and so on, but say nothing, absolutely nothing about this aspect of time, that is time's passage. And the idea is, let's try to make the passage of time something which is explicit within the physical formalism and see what we get. So here is the outline. I'm going to criticize the present dogma in physics, which denies any becoming, and I'll show why becoming must be there in the formalism. I'll consider the two extreme alternatives, and I'll try to show that none of them is good. Then I'll take a clue from quantum mechanics, which gave me the inspiration for the present idea. Then I'll introduce the hypothesis of becoming and its consequences, which are quite many. It has bearing on the nature of the space-time, the quantum mechanical wave function, relativistic effects, and even clues for field theories. What is the common view of time? We believe that the man in the street tells us that there is something about time, that events come and go. There were tyrants who were born, committed their atrocities, and died one after another. This is something about time which you don't see in space, the succession of events one after another. That simple view of time is almost forbidden in the physical formalism. Consider the nature of space, for example. It would be arrogant and ridiculous to say that only Canada exists now and Japan or India or Israel do not exist, just because they are not given to our experience. All places, all sites, all locations have the same degree of existence, and each of them is accessible to the persons residing in that place.
You say the relativistic view, but what time are you talking about? Because there are many different times.
I'm talking about the Minkowskian. Yeah, I'm going to talk first about special relativity, about the fact that according to special relativity, you should look at time just as you look at space. It would be silly to say that the present time is real and the past is not real and the future is not real in some absolute sense, because there is no privilege now, and you should think about space-time as one four-dimensional continuum in which all events in space and in time have the same degree of existence.
I was trying to get it. Are we allowed to? I mean, should we discuss now?
Yes, yes, go ahead.
So space-like separated events can be ordered in different ways. So
very good.
Can't say that space-like separated events, one happens and then the other happens.
That's exactly the next example I'm going to give, which actually I think endorses the block universe view of time, which denies any reality to a moving now. Just bear with me a second and I'll show what I mean. I argue that the Minkowskian picture of time, which is part of the relativistic formalism, tells us that all events have the same degree of existence, past, present, and future, just as all locations have the same degree of existence along space. And let's look at the nice exercise known as the Barn and the Pole paradox, which is the spatial analog of the twins paradox. Here you have a spacecraft and a tunnel at the same length. Now you let the spacecraft travel with a velocity close to that of light through the tunnel, and by the Lorentz-Fitzgerald contraction, it contracts. So there is a certain time in which the entire spacecraft is within the tunnel. This, however, is special relativity, and you are allowed to look at the process the other way around. That is, here is a stationary spacecraft, and the tunnel is moving towards it with a velocity close to c. So this time it is the tunnel that contracts, and there is a certain moment in which both ends of the spacecraft are out of the tunnel. So here you have two accounts which seem to be conflicting. Not so when you correctly apply the relativistic picture. You should look at both ends of the spacecraft with all their moments as having the same degree of existence a long time, the same about the tunnel. So the difference is only how you choose your now plane, which depends on your motion. So from the spacecraft reference frame, I would say this is the now. So the two events in which the rear of the spacecraft is already within the tunnel and its front is not yet out, that is the now from the reference frame of the spacecraft, and that is the now from the reference frame of the tunnel. Both of them are equally valid. You have all events along in space-time, and it is just a matter of choice of the now plane. So the Lorentz-Fitzgerald contraction is only one example of the block universe being inherent to the relativistic description of processes. So that is what the block universe account of time. All events, past, present, and future, have the same degree of existence. There is no privilege now, and you can see why people are very careful to avoid this kind of moving now. There is, of course, yes?
I mean, if I open a book on special relativity, right, typically it doesn't have any statement in it like the past, present, and future all exist, or any other statement like that. So what does it mean to exist, right?
Well, I'll go the other way. I'll try to consider what happens if you believe that there is something which is a privilege now, and it moves. It will lead to so many contradictions that then you will see that the default, the block universe, is the only alternative. But let me for a minute only consider the other extreme, which is presentism, which is held by a very small minority in physics. These are people who will say, well, let's take the man in the street account and say that only present events are real. Then the idea of a four-dimensional space-time and notions like world line and so on are mere metaphors. It's only nice mathematics, but you shouldn't take it seriously. Take seriously only present events. And I would say that the cure is worse than the disease if you try to say that space-time, this four-dimensional manifold, is only a mathematical abstraction. You are losing one of the most important insights of general relativity. Space-time is general relativity tells us that space-time is a physical quantity physical entity which interacts with masses and gives rise to the curvatures, the singularities, to the black hole. You don't want to give up space-time as a real entity and say that only present events are real and this is only nice mathematics. So why do most physicists deny becoming? I think that may answer your question here.
Okay, I was going to try and defend present.
Okay.
Well, what if we just said, I mean, there's a particular Lorentz frame and only things on a particular space-like surface is real. What does that add or subtract to physics? I mean, it seems to me they could say that. It doesn't make any difference to any measurements. It's just there's an extra term in the theory which is real. Good. So why can't they do that?
Good. Let's do that. It would be nice to consider that. I mean, when I consider the block universe in the search for a unified theory, I see that it is of little help. That's my opinion. I think I can show that if you take the other extreme, which is presentism, and try to see what it has to do, what it has to offer you when you are trying to unify quantum mechanics and relativity, it offers also very little. On the other hand, I will try to show that becoming, which takes some essential clues from both extremes into something new, has something to offer.
Okay.
Totally.
But will you be able to say that presentism and block and becoming differ in their observable predictions?
Had I been able to produce a single refutable prediction for my theory, I would be singing it from the rooftops. At present, it is a model, it is not yet a theory, but you can never know.
You mentioned that there were a small number of physicists that believed in presentism. I don't never met one, although maybe.
Presentism? No, not really.
No, not really. No, I don't know.
Yeah,
Where is many presentism in
well,
real?
there are lots of
What?
There are lots of philosophers believing in presentism.
But do they predict any different observation?
No, no.
Why can't they do it? It's just a-
So let's continue. Why do most physicists deny becoming? They'd say it might entail a higher time, how fast does the now move, and so on. So you will need an infinity of times. It seems to entail, for some, absolute simultaneity. That was the reason why Gödel avoided becoming and made a very strong statement in favor of the block universe.
Good?
Gödel. Now, I want to make a comment about the lavishness of present-day theories, how generous they are in invoking extra spatial dimensions. Think about string theories, how they talk about hyperspaces, multiverses. Think about the present theories about brains, floating in some hyperspace, colliding with one another, giving rise to the Big Bang. Is there some hypertime, some higher time or hyperspace or something like that? You have many kinds of theories like that which are very generous, almost extravagant in invoking these kinds of extra dimensions. All of them within the block universe. Nearly none of them is trying to make use of the idea of real becoming and see what it can help you in your search for a unified theory. So let me mention a few quantum peculiarities, few quantum effects, which are actually temporal peculiarities, which I think could be a good starting point for the theory that I'm trying to advocate. We all know the EPR experiment in quantum mechanics, which is a spatial paradox. We know the double slit experiment, which also seems to present a certain paradox about space. But then there are paradoxes that have some bearing on the nature of time. Think about the delayed choice experiment, in which at the last moment you can take out the second beam splitter and decide what kind of a history you are actually observing. Then there is the Henry-Brown twist experiment, which I'll describe a bit later. You might be surprised to see that the Schrödinger cat is a temporal paradox. And I got this idea from a student who once asked me a naive question, which turned out to be very profound. She asked me, why do you guys think that there is a paradox about the Schrödinger cat? The question seems to be, if the cat has been sealed in a box for a long time, we don't know whether it has, and then we open the box and find whether the cat has been is dead or alive. Then there is a possibility that the cat has been superposed during the time in which the box was sealed. But that student asked me the following question: suppose that the process is long. So here you have the cat and the deadly machine sealed in a box. After a while, when the box is sealed, the lethal event occurring or not occurring, but that happens at the very early stage of the process. Then you wait for, say, a day or two, and at the end, when you open the box at T final, you either get a dead cat, but which is decomposing, so you know that it has been dead during that time, or you find an alive cat, but lean and very mad at you, so you know that it has been alive all that time. So there was no superposition. By just looking at the cat, if you make the process long enough, you know that it was not in a superposition. And it took me a while to reflect on the problem in order to understand that the question to her answer is that the observation made at the end of the experiment is actually determining not only the state of the cat at that moment of opening the box, but its entire history. So this is one of the cases in which measurement determines not just a state, but all the succession of states before that, that is the entire history. So I would argue that this is another kind of a temporal paradox, which should give us an inspiration to rethink about the nature of time in quantum mechanics and in physics in general. So let me introduce to you an experiment which we developed, which brings this feature of quantum mechanics, makes it very strong. Here is an effect known as the Henry-Brown twist effect, which is about interference. You can have interference between photons who come from different sources. If you take care of the geometry, and then you have two sources equally distant from a beam splitter, if you place them correctly, then you can have you have to make the two sources coherent, and then you can have once the light coming from the two sources is split by the beam splitter, you have the waves in phase on one side, out of phase on the other side, so you have all the light coming to the same detector. What is
the
amazing?
sources are incoherent, right?
Excuse me?
The two sources are not coherent with each other, right? That's the point.
Okay, but it is a special arrangement that you have to take in order to get this information.
I'm just clarifying.
Okay.
It's not coherent light emitted by two sources coherent one to the other.
Right. Okay. Now, what is amazing is that this thing holds even at the quantum mechanical level. So if the two sources is dim enough so as to emit a single photon, say every 5 minutes or every hour, then even those single photons would be registered always by the same detector. So this is a very peculiar situation. You can think about other particles, perhaps even neutrons or other, such particles which we know to be particles, coming from two sources. So you have a single particle every once in a while, but that particle seems to have come out of two sources, which is really very counterintuitive. You have here two histories about which you are uncertain, and that uncertainty is enough to give you this interference between the two sources. The next thing I'm going to introduce is a beautiful experiment devised by Hardy many years ago. You take an atom, you prepare the atom in a spin-up state in the y direction. And then you send it to a Stern-Gerlach magnet, which is aligned along the x direction, such that if it is x up, it goes to the left. If it is x down, it goes to the right. So actually the wave function is split into two. Now you see the two halves of the wave function in two boxes. The boxes being transparent for photons, but opaque for the atoms, so the atoms cannot escape. So I christened this kind of atom Hardy atom, because Hardy managed to do a beautiful experiment with this kind of atoms. You take a Mach-Zehnder interferometer and place such an atom on one of the arms of the interferometer, such that one of the boxes is on the arm on one of the possible routes of the photon, and it arranged in such a way that if the atom turns out to be in that intersecting box, that is here rather than here, and if the photon turns out to take this path rather than this path, then in 100% of the cases you have absorption. This is a Gedanken experiment. You don't have to worry for the technicalities. Now, if you place two such Hardy atoms, one on the right and one on the left, and you get a click here on where you should not get a click, has there been interference, then the two atoms are entangled in a way in which I will show in a minute. So here is a nice experiment in which two atoms, which never interacted in the past, become entangled, and they are an EPR pair. You can test them for Bell inequality violations just by virtue of the fact that a single photon could have interacted with either one of them. Take the Henry-Brown twist experiment in its quantum mechanical version, and take a Hardy atom, and you get the following experiment, which Dolev, Zeilinger, and myself proposed a few years ago. It is a kind of a time-reversed EPR. You make the same setting for the Henry-Brown twist experiment. So here you have two sources of photons, one here and one here. And has there been no atoms here, then always you will get a click here when you see interference. And then you place two such Hardy atoms on the two sides, on the two possible paths of the single photon which you register. Then here are two Hardy atoms, they are in a superposition, but not entangled. Then and photons through the system. Remember, the sources are very dim, such that you have single photons every once in a while. If the forbidden detector flips, that is this one, then you know that interference has been disturbed. That is, one of the paths is blocked. It couldn't be both of them, because then you would get no photon at all. It couldn't be that both atoms are in the non-intersecting boxes, one here and one there, because then you would get interference. So you are left only with one choice. Either the left atom has blocked the photon and was in the intersecting box, but that means that the other one was in the non-intersecting box, or vice versa. That is enough in order to create entanglement. The two atoms which were not entangled to begin with are now entangled, and they can violate Bell's inequality. So here you have an EPR experiment in which the entangling event is, so to speak, at the future of the two atoms rather than at their past. So it is a kind of the time reversed EPR, which my colleague Shahar Tolev proposed to call RPE because it is time reversed. Now here comes a paradox. Let me remind you, and sorry for the technicality, how you measure for Bell inequality violations. You subject the two particles, or two atoms in this case, to 1 out of 3 measurements. We should call them in this case 0 degrees, 30 degrees, or minus 30 degrees, and you see what are the correlations between them. The most surprising case is the third group, in which they are aligned such that the angle between them, the relative angle between them, is 60 degrees, and then the correlation drops down to 25%. This is something that you cannot get by any local theory, which means that each of the two particles kind of knew which is the measurement to which the other is subjected, which was the result, and it knows when to give conflicting results. This is Bell's famous proof for non-locality, which leads to the following paradox. I'm repeating the experiment that I showed earlier of the time-reversed EPR, and you get something like the quantum liar paradox. Here we are. We have two Hardy atoms, one here and one here. We have the two sources giving rise to a single photon. And now to prove non-locality, you have to do with the atoms one of the two things. You use spin measurements in 3 directions. We shall call them again 0 degrees, 30 degrees, and minus 30 degrees. And now you have to you run the experiment many times, time and again, and subject each of the atoms to 1 out of these 3 measurements at random. So every once in a while, you will have to measure the 0 degrees, which means that you are just opening one of the boxes. You inspect the 2 boxes and see in which of them the atom resided. In the other cases, however, you do this. You realize the boxes. You lose any information about which box, about the atom, whether it was in the intersecting on the non-intersecting box. You realize the atom, then split it again along one of the 2 other directions, and then make the measurement. So you run the experiment many times, again and again, subject the atoms to 1 out of these 3 measurements, one of which is the which box measurement, and then you prove for Bell inequality violations. But here is something interesting. In some cases, in 1/3 of the cases, you subjected one atom to the which box measurement, and you sometimes find that it was in the intersecting box. I'm showing here this atom, and you find, if you make a measurement, you find that it is in the intersecting box. That means that this one was in the non-intersecting box, which means that actually no photon could have gone through this path, which actually tells you that there could be no entanglement between them, because there is no any physical connection between them. There is no any event which entangles them if a photon couldn't pass in one of the routes. Then in some other cases, you use another measurement on the other box. And you see that there are Bell inequality violations, which is very strange because that means that the kind of decision of the first atom to be in the intersecting box and block the photon so as to deny any kind of entanglement with the other is in itself a result of the entanglement, and you get the following, you end up with the following history. One atom is found to have blocked the photon's path. Hence it appears that it could not interact with the other atom, and therefore should not have been entangled with it. But by violating Bell's inequality, that very state of having blocked the photon was affected by the measurement of the other atom, which is logically equivalent to saying something like, it's a kind of a quantum mechanical paradox. That may make it a bit more sharp. There is another way that you can do this experiment, and this is due to Zoller and Sirac, who actually performed this experiment. But you can show that the same paradox applies here too. You have here two atoms in two cavities, and the two atoms are in an excited state. This one and this one. They're in an excited state, so one of them after a while is bound to emit a photon. Then you wait for a while until you get one of the detectors clicking after the beam splitter. It doesn't matter which of them. It is enough that you don't know whether the photon came from this atom and just passed the beam splitter, or whether it came from this atom and was reflected by the beam splitter. Once again, you have uncertainty about the origin of the photon. So then, either one atom is excited and the other is in ground state, or vice versa. That is enough to entangle the two atoms. They are now entangled, and they are an EPR pair. That is, you have to find now another measurement, which is orthogonal to the measurement of ground and excited, and you run the experiment many times, and you find Bell inequality violations. But here, once you have an EPR experiment, you have the Lyell paradox all over again, because here is what you get. One atom is found to be excited, which means that, which seems to indicate that it emitted no photon at all. But then it could not interact with the other atom and should not have been entangled with it. But by violating Bell's inequality, it's being in the very state of that atom, having preserved its photon, is due to entanglement with the other atom. So once again, you have the kind of Lyell paradox in the quantum mechanical version. I argue that this is an interesting paradox in the sense that it does not involve only a contradiction between quantum mechanics and relativity, or quantum mechanics and classical physics. But here is a case in which nature is telling you a story which is inconsistent within itself. So it tells you how paradoxical quantum mechanics is. I should say that this experiment is one out of a family of experiments. Another one being due to Shachar Dolev and myself, and many others by Aronov and his group. What is common to all these experiments is that a single particle is subjected to two measurements, and at the time between those two measurements, that particle produces all kinds of bizarre properties, such as a single particle going through a Mach-Zehnder interferometer. The particle goes on one arm, but there seems to be some indication that its charge is on the other arm, and other such paradoxical effects. Some of them are now being experimentally tested. Let me quote what Yatir said to me in private communication, his view about time. Every quantum event is visited twice. You know that Aronov has a special formalism of quantum mechanics. He calls it the two-vector formalism. According to that formalism, you should view any quantum mechanical event as the result of two wave functions, one going from the past to the future, the other going from the future to the past. So in that state between measurements, you can see some peculiar phenomena. Now, his personal belief is that every quantum event is, in some very real sense, is visited twice. Once by the state vector coming from the pre-selection, and then the other coming backwards from the post-selection. So he does believe that every event in space-time has a history in space-time. So that there is something more than just time being the coordinate, but something deeper. And this is what I'm proposing, how to interpret these results.
Can I ask you a question?
Yes, Joe.
All the paradoxical results that quantum mechanics implies imagine magically somebody produces a local invariant theory. And imagine the universe in which Bell's theorem is just non-existent or wrong. Would all the implications you suggested be still valid? Or
You're asking, has there been no prohibition against velocities greater than light?
no.
No, okay.
Nothing about special.
Okay. Has there been hidden variables?
Yes. If you produce a local invariant theory,
I believe-
in a universe where Bell's theorem is not valid, would all the paradoxes follow?
My answer is offhand, but it would be yes. I
Still
should think.
surprising, even with local invariant theory.
Yes, but there will be such hidden variables, but they would be operating in a peculiar way. And let me show you what I have in mind. If you look at the Bolshaya Sovietskaya Encyclopedia,
Is that a little out of date, Sovietskaya?
well,
Sovietskaya is a little out of date.
yes. Yeah, Jim, you just caught the essence of what I'm going to say. The Bolshaya Sovietskaya Encyclopedia has a large entry about the dedicated the large entry to the Bering Sea. And the question is, why should
You know why it has such a large entry? Oh, I'm sorry.
it talks a lot about the Bering Sea. And the question is, why should the Soviet Encyclopedia give such a long discussion, such a long description to the Bering Sea? Well, if you go to earlier versions of the Soviet Encyclopedia, dating back to the times of Stalin, you would see this guy, Lavrenti Beria, who was then the hero of the people, the head of the KGB or Cheka or something like that, who featured prominently in the Soviet Encyclopedia. Then came other times, the guy vanished and he stopped being the hero of the people, and you had to purge him from the history, so people went to the houses of Soviet people, asked that volume in order to take out any mention of Beria. But then what do you do with all those pages which are remaining? So this is how the Bering Sea came and covered any trace of that hero of the people. Is it possible that nature is doing something similar of rewriting history? That is it possible that processes are sometimes reiterated? That there is, and here I am following Kramer and Aronoff in invoking this kind of advanced and retarded interactions between events. Is it possible that sometimes you see traces of that reiteration which give you the impression of some inconsistency in the process that you are observing? From now on, this is the road less traveled, and here is where I'm going to propose my hypothesis. If the passage of time is such a prominent feature of time, then let's stop explaining it away or deeming it a mere illusion and say that there is something in time that should be represented in the physical formalism. So here is the assumption of becoming. Very simple. Events are created anew, one after another in space-time according to the causal order. At any moment in time, which one perceives as now, future events are not only unknown, but objectively inexistent, and then they will, in some real sense, be created as the now kind of advances. Now I know, it's one thing that I was thinking immediately when proposing this hypothesis. People are talking about compact dimensions. There are extra dimensions, but they are compact. But becoming could be the ultimate compactification. If there is some real sense in which the now is going upwards and creating new events, then what we see in every state of the universe is just the end product of this creation. But what happened in between, in some higher time, we shouldn't say higher time, some deeper time, that we cannot know. So that is the place where some of the mysteries could be hiding. And who knows, that might make some extra dimensions or many extra dimensions unnecessary, because time itself is now being compactified by the very assumption of becoming.
The extra dimensions are to represent typically internal symmetries. That's the usual application.
Right. I don't know, I didn't try it, but is it possible that you can do the same thing with becoming and introducing some new symmetries?
I have no idea.
Me neither. It's a hypothesis.
Well, there's the F theory of Wafa has an F theory, which is extra dimension, which is a variant of M theory, actually. predecessor time field.
Well, the typical application, right, is you have a small number of extra dimensions at each space-time point. The symmetries that internal manifold molecules apply manifest the symmetries of the effective branching flat number of dimensions. But anyway, this is not central to you.
But
Don't.
I'm not actually following. What is the connection between compactification and becoming?
I see. If you describe, it will become clear later when I'll talk about space-time growth. So here is something that I'm taking from math. You know, if there are no events, there is neither space nor time. You can't talk about space or time without any events. So that means that if you argue that future events do not exist, that means that there is no space-time beyond the now. There is no space-time in the future either. So at any event, it is not only that there is some space-time, empty space-time in which events will grow later and will become, but there is no space-time beyond the now, which means that space-time seems to be in some real sense growing in the future direction. Now that has a cosmological ring to it. Space-time is preceded and bounded by nothingness, just as there is nothing outside of space-time. You can't ask what is outside of space-time. You can't ask what is outside of the now. There is that ultimate nothingness. And I want to show that the reason why people were avoiding becoming should not worry us here, because people say, if you believe that there is some time which advances, if you believe that there is some now which advances along the time dimension, then you should ask, is there some higher time dimension? Is there some extra time? Now, of course, that would give you an infinity of times. Now you remember that I thought that the presentism would be a too radical move if you want to avoid the block universe, because then you are giving up the beautiful relativistic picture of space-time with all the effects following from the existence of space-time. That should not worry you when you are talking about becoming. You can now apply presentism to the movement of the now, which creates the time, and you don't have to worry about something relativistic being lost, because we don't have a relativistic theory of 5 dimensions or something like that. So I want to argue that this move does not get you into the problems that it would get you have you been employing presentism when you are talking about space-time.
But what is it?
Yeah. The picture that you're seem to be presenting of now moving forward, it seems to be completely wrong as far as relativism is concerned. I mean, there is no universal now in
Sure.
moving forward. So that something much more refined has to be.
Absolutely. We want to make it relativistic, but that will be the next step. You don't have to deny that. That will be the other degree of freedom that you are introducing. Let me just point one difficulty that we have. Yes.
What is it moving with respect to? I mean, the space-time, of course, can have a boundary. So you can have a space-time that has...
I said that it's not a motion. I said that it's a growth of space-time. So
what is it growing with respect to?
with growth, you can say that it is growing with respect to itself. I mean, just as you say that when you talk about space-time expanding, you are not invoking some higher space within which space-time is expanding. You look at the distances between events within space-time when you talk about the universe, and the distances between them grow. You don't have to invoke a higher space in which the universe is growing. Something similar you can do if you believe that it grows also in the time direction. You don't have to invoke some higher space. So it's not a real motion. We are careful to avoid that. We are taking the lesson of the Big Bang and talking about space-time, which is the whole story, but within itself, it can grow.
Well, expanding the universe, right? I mean, it's expanding with respect to viewed in a 3+1 sense. Space-like surfaces, the space-like surfaces are getting bigger with respect to some time, which labels. But it seems to me you're saying that the manifold has some sort of boundary, right, which is supposed to change.
Let's do this. If you get further and further from past events, okay, then your now is becoming more and more far from yesterday or from the day before yesterday.
Me personally, right, getting further and further away from my Earth, for example, which is happening all too quickly. Yes, I agree with that, but that doesn't mean the space-time is a boundary. Am I supposed to envisage a space-time with if it was general relativity with some boundary, right? Time space like boundary?
Is the now kind of a boundary? I'll try to show what kind of boundary it is, and then tell me whether you have it. But then, here's the problem that I encounter. You know what Kant said? Time and space are necessary forms of any thought. Well, we can talk about PowerPoint presentations. But then, you know, every time that you think about any thought that you think about, you think about space-time. So when I'm talking about the now creating time, I cannot help thinking about some outer space out there. This is the problem that we all have when we talk about the Big Bang model. So I cannot avoid it. And here is another philosopher who said, never specialize time. He said that because every time that we talk about time in a mathematical way, we are treating time as if it is space. And those problems, which I cannot overcome here when I'm using PowerPoint, are inherent to any kind of graphical presentation. So let's be aware of them. First of all, we are talking about block universe. So here you have trajectories of various objects which interact with one another, and here you have past, present, and future, all of them existing. What kind of becoming would you like to envisage? So here is, again, the problem. That black area which I'm presenting is still spatial, and we should not do that, but there is no way to avoid that. So I would say that that is the now, and I'm not claiming that that now is universal. We will have to make it relativistic. And then it could be some kind of growing space-time in which the now creates more and more events, so space-time seems to be growing in the future direction. That is the kind of possibility that we are trying to think about, but then we want to make it, to put more physical content in it. And here I propose, let's think, yes, Joey?
Before we go to quantum, I mean, the very fact that we are talking about this process comes from our immediate experience of time moving forward. So it comes from that phenomenology that you are trying to put into physics. Now that phenomenology is restricted to local now along the world line of each observer. There is no such thing as post-Einstein, there is no such thing as now.
That is the problem which you encounter every time that you try to invoke becoming. Is there some universal now, or can you avoid it? I'll try to show that you can avoid it. I won't be able to present a specific way, but in general, I'll be able to point out how you can avoid it.
But it's still thinking that before you go into the quantum, right? I mean, you have a description of this that's completely intrinsic to the space-time. I mean, as I watch that dark line go up, it's going up at a certain rate, measured by my watch, which is not in the black hole. Right? So you have a sort of intrinsic description of it, right? That doesn't need any external.
I think that it does not, for the simple reason that people. I think that it does not need an external time for the simple reason that we consider presentism when we talk about space-time. And then people don't have this problem by saying that it's only the present that exists. Now, if you take this four-dimensional manifold and you invoke presentism to that, I think that you can manage to avoid a higher time. But let me see if that is possible.
I have to say, I don't get it. Right? Maybe it'll be
Okay, let me see if I'm asking these same things slightly different way.
Yes.
Julian Barber uses this sort of picture where you have a camera, you go and take lots of pictures, and you stack them up, and then you shuffle the deck. How do I stack the deck? And I can stack it different ways after different shufflings, and I don't know what is growth and what is not growth.
Completely different picture. So
I think that he's, I must confess that I haven't read Barber yet, but I think that what he's proposing is a kind of elimination of time. So that is arbitrary. I would say that the way you shuffle the cards is arbitrary, whereas what I'm presenting here is that you shuffle the way somebody is shuffling the cards for you, and in a non-arbitrary way.
But
So
as Jim said, there's this black line going up in a particular.
once again, you think about black lines, so then you think that there is some space. You see, we fail to do what we have to do when we are talking about the universe. You never think that the universe is expanding. You never think that there is some boundary, real boundary, in which the universe goes into some space in which this boundary grows into. Something similar can be done with respect to time.
But can I just add something to pick up on something Jim said right at the beginning? He was asking questions about when you were saying something about existence, you know, things exist for us now. And he was saying, what does that add to the physics? It seems to me that this moving line, the difference between the black and the white is non-existence and existence.
Right.
And so where this sort of space-time is moving into is in some sense like existence, because that's, so to speak, the tag, or the dimension. It's moving along the dimension of existence, if you want to talk about it. That's a rather vague way of putting it. But I mean, the point I wanted, what I'm worried about is, in physics, I don't actually, I agree with Jim, I don't understand what it means when you add the term something, you know, exists, and you kind of bang the table and say, well, that exists as opposed to not existing. I mean, it doesn't seem to add anything to the physics. And so I'm a bit worried that
Here it is.
I don't know how to understand that other than, well, you know, what exists is becoming more or something, you know, and that seems kind of a bit suspicious.
I see. Think for a moment about the moment of the Big Bang, okay? So, there is, in some sense, non-existence and then something exists. Now, any attempt to talk more precisely about what's going on will end up in absurdities. First, there was no universe, and then there was universe. Then, once again, you're committed to time, and you fall again into the trap which Kant and Bergson tried to warn you not to do that. These problems I cannot solve. All I'm saying is that these problems, which hold for the Big Bang, hold for any moment. So that seems to be kind of problematic. Here we have a serious problem which first we thought it applies only to the Big Bang, and now it applies to any moment in our lives. But then it opens several new possibilities. The problem is still there. How do you overcome the conceptual problem of thinking about something coming into existence without invoking some more primitive time, or with invoking, talking about some pre-space-time or pre-geometry or something like that? I don't know. All I'm saying is that these problems exist. Attempts to solve them exist. The research program which I'm proposing is apply them to any moment, and then you will see interesting things happening with quantum mechanics and with relativity theory. I'm aware that there is a problem, and this is why I brought these two gentlemen, Kant and Bergson, in order to show that anything that I show here, any PowerPoint presentation, even though Kant or Bergson didn't think about PowerPoint presentations, because I'm using some space in order to show that, and I'm using some time, I'm in trouble. This is a leap that we have to do beyond space and time, to think that there is something more primitive than space and time.
I mean, it's possible to do it. You can show an observer in its world line, and you can argue that the world line is growing.
Sure,
So
but that's exactly what I'm saying. World lines are growing, but then if there are no world lines in the future, what's the point of talking about space-time? That's exactly the thing. There are world lines. So if those world lines end somewhere, so that means that beyond them there is no space-time. So you have to think about space-time as growing in this way, such as it includes more and more events, and world lines are in some way growing. So here is
a positive remark,
Please.
It may help. I don't know if you're familiar with the work of Raphael Sorkin, right? But Sorkin has this picture where we have the space, time, no, they're just discrete points, the causal networks, and the network grows by a certain set of rules moving forward.
I became aware of Sorkin's.
Is that an example of what you're talking about?
Could be. I must admit that I became aware of Sorkin's work only upon coming to Perimeter. I was coming here thinking that I'm the only guy who proposes such an idea, and I've been told by Joy and others that there is such a work. So I should familiarize myself with that work. I didn't know about it.
Can I answer for you?
Yeah.
Yes and no. Sorting that, and it's got a picture, but it's not a space-time. It's got just a causal set, which has no actually have any content of space-time.
Well, we have a lot of these points.
It's got a causal structure.
Right, then it's supposed to be coming.
And
Okay. I'm nearly
I
there.
got the answer.
I'm nearly there. Can we make it quantum mechanical? And here are all the problems that we encounter could turn into an advantage in the following sense. That's the hypothesis that I'm proposing. Quantum mechanical, quantum mechanical interactions are bizarre. Is it possible that they are bizarre because the interaction takes place beyond the now? That is outside of space-time. Here is the place when we can place those quantum interactions to make them more primitive than space-time itself. And therefore, this programmatic collapse gives rise not only to the particle in its location, but to all the points in empty space where it couldn't be. So we are giving the wave function a more primitive status than the space-time itself. Rather than thinking that there is some empty space or empty space-time within which the wave function is evolving, why not think that the wave function is there before space-time, and there you have the interaction, and once there is an interaction, there is the space-time associated with that. So the space-time associated with an interaction emerges only as its consequence in some deep sense. And now I'm aware that what I'm going to show is going to be ridiculous, but that is again the Kantian limitation that we have. We want to have this becoming, this growing space-time, in a sort of quantum mechanical way. So is it possible that this is what you have? First, those world lines, their wave function interact with one another, and then you have another piece of space-time associated with that, and so on, and so on, and so on. So there is some kind of interaction going on before there was space-time, and this is why you see the non-local or non-temporal effects that you see in quantum mechanics.
That only looks like a Schrödinger equation.
Sure.
So there's no collapse happening there. So there is no time there.
Here's the problem for you. I don't know how do you represent interaction without thinking about space-time? This is the leap that we have to do. The Big Bang cosmology did that. All I'm arguing is let's continue to do that. What do you do with the Big Bang? I mean, how can you describe anything that happened before the Big Bang? I'm saying that the same problem applies as to how do you describe something which is beyond the now. Yes, so this is why I chose this particular thing like the Schrödinger equation, because I don't have anything else. It turns out that special relativity is saying something very similar. The speed of light is more basic than space and time. So that is the thing which is invariant. Is it possible that it is due to the fact that the electromagnetic or gravitational interactions precede the relative positioning of events? So this is why when you look at the whole picture, then you see that the speed of light is invariant, and that is the finite velocity. One more move about which may answer to your question. I mean, if mass gives rise to curvatures in space-time, it can also change this kind of becoming. So now that line of now does not have to be simultaneous, but it could be unique to any reference frame, and it is only the interaction between them which brings out the space-time relations that we know from special and general relativity. So I can conclude with proposing the following. First of all, one of the big questions in physics, the origin of time asymmetry, and there is a beautiful paper by Joy which proposes the same thing. So becoming is the master error of time. And you asked about all those errors of time, cosmological, thermodynamic, electromagnetic. Once you introduce becoming, that becoming is the source of all these asymmetries, which creates the space-time between intervals between events. Let me say only one last thing about position being at rest or being at motion. Position rather than being defined by other positions. This is Mach's idea. Perhaps we can now give it an ontological meaning by saying that the position of objects emerges due to the pre-space-time interaction between these objects. And why I find this fascinating is the following. If the wave function upon measurement gives rise not only to the particle's position and momentum, but to the entire space-time associated with it, then it means that the space-time interaction determines the distances between objects, whether they are closer or further from one another. So the whole notion of attraction and repulsion gets a new meaning in this framework. And the research program which I was proposing and trying to answer your questions is this. take all those theories which talk about what happened in space-time in terms of those extra dimensions, were they compactified at the moment of the Big Bang, or whatever happened to them. There is a family of theories. Why don't you apply these theories to the creation of space-time, which according to the space-time dynamics model, happened not only once, but keeps happening any moment. So whatever those theories are proposing, why not try them on within the present proposed framework? This is the road less traveled, and what I find personally overwhelming here is that it has so many ramifications. Once you introduce the possibility of becoming, then there are so many possibilities that you have to explore that ideally you would need many people to concentrate, and this is why this talk became so condensed, because I was trying to bring in so many possibilities to explore once you introduce this idea of becoming, and once you try to make it part of the formalism. The road less traveled has many forms, which is both a disadvantage and an advantage, and which I think it makes it so exciting. Here's something that Minkowski said shortly before he died. What a pity to die at the dawn of relativity. But relativity's dawn is long over. The sun of relativity is high up in the sky, but there should always be a new dawn and something to wait for. Thank you very much.
With regard to forking, you mentioned these two great Bergson and Kant, but a great American philosopher, Yogi Berra, said, when you come to a fork in the road, take it.
But that doesn't contradict the becoming.
That is just becoming.
Just becoming.
Yeah.
Wow. Take a fork.
So it's a good quote.
Could I ask another question? I mean,
Sure.
Is this consistent with Aharonov's views that the stuff in the future is propagating back to the past, or is it? I mean, it was meant as an implementation of that idea, or is it?
It is inspired by him. Yes, of course. He was the first person to whom I showed this model, and the inspiration came from him. Remember what he says. Do you know Kramer's model, the transactional interpretation of
Only
models?
from listening to your talks.
Okay, so it's strange because Kramer is one of the few leading interpretation makers in quantum mechanics. He has an important paper he published in 1988, the transactional interpretation of quantum mechanics, in which he proposed that in order to understand some peculiarities of quantum mechanics, you should think about interactions going back and forth in time, so you have all these kinds of Feynman zigzags. So he explained beautifully things like the EPR experiment. Think about some advanced influence going from the present measurement back to the source in the past, then coming back to the present and affecting the other particle, and then you are surprised why is there no locality. There is no locality in space, but not in space-time. He was an ardent proponent of the block universe, and in that paper he kept warning the reader, do not think that there is some extra time, some meta time. Aronov, during all that time, invoking a similar model, said explicitly, although he never wrote it, that he believes that there is some deeper sense in which those wave functions go one after another. First, there is a wave function going from the past to the future, then from the future to the past. By the way, there is a historical curiosity. If you look at the Wheeler and Feynman absorber theory back in the 40s, which gave the inspiration for Kramer's transactional interpretation, then they say about advanced and retarded waves. They talk about first there is a retarded wave going to the future. Then there is an advanced wave going to the past. Finally, they say first, then, and finally when they are talking about space. So, of course, you could think that this is a figure of speech. What is nice about the Aharonov's approach is that he believes that there is something missing in the physical formalism, which is needed to describe this consecutive operation of the two wave functions. Recently, Kramer himself admitted becoming and said that he opposes the block universe, and there should be something in which events are really coming into existence one after another. So, to the question, is this consistent with Aharonov's two-vector formalism? Yes, according to our node itself.
Because the future vector lives up there in the part that's not yet become, right? Is that the?
That's what it is.
Okay. And it just, so I can orient myself, is Kramer and Aharonov the same thing or something different?
No, there are differences. Both of them would argue that there are differences. Of course, what
But at a very coarse grained level, just for a peasant like me.
there is, yeah, there are transactional. You can call the two vector formalism transactional formulas. There are differences. What is interesting is that Aharonov took his formalism as a way to predict some surprising, some peculiar results. Now he will tell you that you could get the same results, get the same experiments that he is proposing now by using the existing formalism. But he says that that approach makes things more sharper and enable you to ask new questions.
So just to clarify, when you want to treat each moment of time as a Big Bang creation event in this, and there's no sort of dynamical mechanism available at the moment of how that happens.
Right. This is a model, this is not a theory. Just at the very beginning, I dared to propose it only in the last 2 years, with the hope that in the future it will develop into perhaps into a new theory. So I believe that there is, I believe that the future does not exist yet, and it promises new developments. So we have to wait for the future.
So just one final remark, because I happen to have written an essay that's related to this, right? But it's in some sense a very different point of view. I think it is what you guys would call the block. What?
Blocking.
The block universe. But the idea that all these statements becoming, now, past, present, and future are properties of the specific way we're constructed. And I tried to argue that there were alternative ways of doing it, so that the notions of now, becoming, and so forth would be different, or differently constructed ibises, information gathering, utilizing systems in the universe, so that at least it was an experimental question. As soon as, I mean, the conjecture was it's adapted because of the local laws of physics to make this, to have these notions, and that if we journey to some yet unknown part of the universe, we could test this by finding out whether it was adapted in other places.
So,
There's no response to this.
so you have some predictions. You can derive some.
Sort of predictions. I mean, as soon as we get, not predictions will be realized in my lifetime.
That's what we are all hoping for, to derive predictions from our models. This is how they become theories.
It's a book prediction.
Can I also bring up my paper? You had two questions about, is there an intrinsic way to do this?
Mm-hmm.
And there was another question which was, with respect to what is moving?
Right.
Well, both of these questions are answered in my paper.
Good.
So, the one I gave you.
Consistently, so you would agree with it?
It's a different picture.
We began the dialogue.
Yeah, it's a different picture, but I have mechanism in which both of those questions are answered.
Okay, good. So you gave me the paper, right?
Okay.
So I should read it in your,
Please.
because there's no.
As well as mine. I'll give you mine.
I didn't think I got any papers.
I'll give.